Imagine you just walk into a room, you flip a light switch, and the power just works. We never really think about the massive, totally invisible balancing act happening right behind that switch.
Oh, absolutely. It's just magic to most people.
Right. But what if I told you that to keep that magic working, engineers actually programmed a multi-million-dollar machine to intentionally trigger regional blackouts, like a system built with the sole, ruthless purpose of cutting power to entire neighborhoods without even asking for human permission.
It sounds kind of villainous when you put it like that.
Doesn't it? We tend to think of the power grid as this nurturing utility that just wants to keep the lights on for everyone. But today's deep dive takes us right into the heart of this automated triage system. It's honestly fascinating.
Yeah, it really is. It's the brutal mathematics of survival, honestly. When the grid is seconds away from a collapse, the system doesn't try to save everyone. It aggressively amputates the limb to save the body.
Amputates the limb.
Yeah. Wow.
And to unpack this, we're looking at a brilliant technical source from a veteran engineer, Sir Abrar Ali. We're going to explore a really critical piece of grid tech called the under-frequency relay.
Which is such an important mechanism.
Totally. But what's great is this isn't just some dry engineering manual. It is a story about grid physics, automated triage, and surprisingly, how to battle professional inferiority complexes on a global stage.
Yeah, that pivot in the source material is amazing. It connects the mechanical nuts and bolts of the grid to the actual human experience of the engineers who build it.
Right, so we're talking physical safety nets, but also psychological ones. Let's just jump right in. Because before we could appreciate this safety net, we have to understand the tightrope the power grid is walking every single second.
And it is a very, very thin tightrope.
Extremely thin. Sir Abrar Ali outlines these strict operating limits in our source. The grid operates within a variation of just plus or minus 5%. So if the system is targeting a baseline of 50 hertz, the absolute lower limit, the red line, it's 49.5 hertz, and the ceiling is 50.5.
Right, and it's so important for listeners to know we aren't just talking about abstract numbers on a digital screen here.
Exactly, it's physical.
Highly physical. That electrical frequency is directly mechanically tied to the speed of these massive multi-ton metal generators spinning inside the power plants.
So they are locked together.
Completely locked. If the massive steel rotor inside the generator physically slows down, the electrical frequency pulsing through hundreds of miles of transmission lines drops in exact proportion, instantly.
Okay, so I was trying to visualize this mechanical load thing, and the best analogy I could think of is pedaling a bicycle.
Okay, I like that.
So imagine you're on a bike, right? You're cruising on a flat road at a really steady, perfect speed. Let's call that steady rhythm 50 hertz. Everything is just humming along.
Sure.
But you hit a steep incline, or maybe someone suddenly jumps onto the back pegs of your bike. That represents a huge surge in power demand hitting the grid.
A sudden weight.
Exactly. Because of that sudden heavy load, your pedaling physically, involuntarily slows down. You can't help it.
That translates perfectly to the grid, honestly. If a massive industrial plant suddenly brings all its heavy machinery online at the same time, the weight on the grid increases that exact millisecond.
And the generators actually feel that.
They absolutely do. Those massive physical turbines at the plant actually start to bog down under the electrical burden, and the frequency immediately starts to slide down from 50 hertz.
Okay, so reading through the source, the way they talk about hitting that 49.5 hertz lower limit, it sounds like absolute doomsday.
Oh, it is. It's a huge crisis.
But mechanically, why? Because if my bike slows down, I just lose some momentum, I don't explode. Why does the power plant machinery face an existential threat at 49.4 hertz?
Because unlike your bike, power grid generators operate in a synchronized network. They are all locked together magnetically.
Magnetically locked, okay.
Yeah, so if the frequency drops past that 49.5 hertz threshold, those enormous multi-ton generators are at extreme risk of going what engineers call out of step with the rest of the grid.
Out of step, meaning they just lose the rhythm of the network.
Well, it's much more violent than just losing rhythm.
Yeah.
When a generator goes out of step, the opposing magnetic forces within the machinery fall out of alignment.
Oh, wow.
And that creates massive, violent mechanical torque. I mean, we are talking about rotational forces strong enough to physically shear the solid steel shafts of the turbines.
Are you serious?
Yes, it can literally tear the multi-million-dollar machinery apart from the inside out. It's a hardware survival issue at that point.
That is terrifying. So avoiding that lower limit isn't just about preventing the lights in my house from flickering. It's about preventing the power plant from shaking itself to pieces.
Exactly.
So that brings us to the real-world catalysts. Like, what actually causes these sudden drops? Our source notes that it usually stems from massive system disturbances, or when a huge load is just forced onto the system.
Right, like the height of summer.
Yeah, millions of air conditioning units kicking on all at once.
Yeah.
Or maybe routine maintenance where a generator is offline, so the others have to carry more weight.
Or unpredictable faults. A lightning strike hitting a major transmission corridor, for instance. In all those scenarios, the demand for electricity vastly, and sometimes instantly, exceeds the available supply.
Okay, but here is where I kind of have to push back on the operational logic a little bit.
Sure, go for it.
We know summer happens every year, right? We know demand spikes when it gets hot. If grid operators see a massive heat wave in the forecast, why can't they just spin up an extra dozen turbines to keep the momentum up? Like, just generate more power in advance.
It's a great question, but it comes down to the brutal economics and the physics of alternating current. Generating electricity is incredibly expensive.
Right.
But more importantly, you cannot store it on any meaningful scale. Utility companies can't just put power in a warehouse. The electricity lighting up the room you're sitting in right now, it was generated the exact millisecond you consumed it.
Wait, really? So running a bunch of massive backup generators just in case someone turns on their AC unit would be financially ruinous.
Completely ruinous and
Yeah.
highly inefficient. So instead, operators do aggressive forecasting. If a heat wave is coming, they schedule manual load shedding.
Rolling blackouts.
Exactly. Plan rolling blackouts to manually ensure the total demand stays below the generation capacity. They purposefully turn off specific zones.
But manual shedding is pre-planned. The crisis scenarios Sir Abrar Ali is outlining in the breakdown, these aren't gradual heat waves. They are instantaneous.
Right, and that's the crucial difference. If a lightning strike takes out a major interconnector, the power it was carrying instantly reroutes to other lines.
So it acts like a sudden crushing weight on whatever generators are left.
Yes, and the frequency can drop from 50 hertz to 49.5 in a matter of seconds, sometimes fractions of a second.
Oh, wow.
A human operator sitting in a control room, they can't physically process that drop, decide which city block to turn off, and execute the command before the machines go out of step.
The bike crashes before your brain even registers you hit a hill.
Exactly. Human intervention is vastly too slow.
Which is why the grid requires an automated superhero.
Mm-hmm.
Which brings us to the real star of the source material today, the underfrequency relay.
The silent sentinels of the infrastructure.
I love that phrase. So these relays are strategically linked across substations, attached to specific transformers or entire radial lines.
And just for clarity for the listener, a radial line is basically a one-way street of power.
Right, branching outward from a substation to feed a specific zone, like a residential neighborhood or an industrial park.
Yeah, and the relay just sits there, constantly, obsessively monitoring the frequency of the incoming power.
And the precision is wild. Sir Abrar Ali mentions 49.6 hertz as an example setting point for these relays to initiate a trip.
Yeah, 49.6.
That is a deliberately placed tripwire, right? Just above the absolute doomsday zone of 49.5.
Exactly. It's the automated triage threshold. If the relay detects the frequency hitting 49.6, it executes a trip command instantly.
It just cuts the power.
Instantly. It might trip one transformer or sever an entire radial line, blacking out thousands of homes or businesses with zero warning.
And by instantly shedding that excess load, the weight is removed from the struggling generators.
Right, which allows the grid to normalize its speed back to 50 hertz, saving the physical hardware.
It's just wild to realize the ultimate technological solution is literally to intentionally cut power. It highlights this uncompromising hierarchy. The survival of the larger network will always supersede localized power continuity.
It has to, because if that relay hesitates for even a second, the fault cascades. One generator goes out of step and aggressively trips offline to save itself.
And then the remaining generators have an even heavier load dumped on them.
Exactly, so their frequency plummets even faster, they trip offline, and it's a domino effect. Within seconds, a localized fault spirals into a total regional blackout.
And restarting from that takes days, right?
Oh yeah. A black start can take days or even weeks to bring the whole system back online from scratch.
Okay, so obviously this triage logic is brilliant.
Mm-hmm.
But what really blew my mind reading this source is realizing how long engineers have been hardwiring this.
Right. The historical context is fascinating.
We are so used to microprocessor-based smart grids, running algorithms. But Sir Abrar Ali details how he personally commissioned these exact under-frequency relays back in 1974 and 1975.
Yeah, right at the start of his career, he was installing Brown Bovary relays, which is just such a fantastic historical detail.
Brown Bovary.
Yeah, it was this legendary Swiss engineering company, one of the true foundational pillars of early electrical infrastructure. They eventually merged to become the modern conglomerate ABB.
Oh, okay. But I am honestly fascinated by the mechanics here. If you don't have a modern solid-state computer chip running digital calculations, how does a literal metal box from 1974 detect a frequency drop of a fraction of a hertz and instantly execute a blackout?
It's incredible, isn't it? Electromechanical relays are just marvels of physical engineering. Instead of microprocessors, they relied purely on magnetic fields and physical movement.
Physical movement, like moving parts inside the box.
Yes. Inside the casing, there's an induction disc. Basically, a literal spinning metal wheel, usually made of aluminum.
Just an aluminum wheel.
Yeah. And you have electromagnets positioned around the disc. One responds to the voltage, and the other responds directly to the frequency of the incoming power.
So the magnetic pole is literally tuned to the 50 hertz rhythm of the grid.
Exactly. When the grid is running at a perfect 50 hertz, the magnetic torque on that spinning disc is perfectly balanced. It stays in a neutral position.
Okay, but then the heavy load hits.
Right. The moment the frequency drops to, say, 49.6 hertz, the magnetic flux generated by the coils actually shifts.
Oh, wow.
This creates an imbalance in the magnetic force, which physically rotates the aluminum disc.
And that rotation triggers the blackout.
Yeah, as the disc turns, it swings a metal contact arm. When the arm hits a specific physical set point, it closes an electrical circuit. That fires the trip command to the circuit breaker, physically severing the power line.
That is just, it's entirely analog. A physical wheel turning a physical arm to trigger a blackout, all calibrated by hand 50 years ago to detect a 0.4 hertz variation.
It's pure, elegant engineering.
It really is. And Sir Abrar Ali mentions doing this at K Electric in Karachi. And the historical context he provides there about K Electric versus the larger national utility, WPA, is super interesting.
It really challenges a lot of assumptions about how infrastructure actually develops. We tend to assume technology rolls out uniformly, from the top down.
Like the national government gets it first, then it trickles down to the cities.
Right. But in reality, localized, dense urban utilities often outpace massive national grids.
Which is exactly what happened here.
Yeah.
The breakdown points out that K Electric, because they were managing the highly industrialized urban center of Karachi, was an incredibly advanced company at the time.
Very advanced.
They were deploying these Swiss relays long before they were widely adopted by WPA, which had to manage this sprawling, mostly rural national grid.
Right. WPA obviously grew to be much stronger and more robust later on.
Sure. But in that specific era, K Electric was pioneering the tech. Sir Abrar Ali even notes that they had advanced telemetry systems operating before 1970.
Telemetry meaning they were remotely transmitting real-time data from distant substations back to a central control room.
Over 50 years ago.
Yeah, and understanding that dynamic, that regional utilities can act as incubators for advanced tech, it provides such a vital lens on engineering history.
Which honestly brings us to the true motive of this entire breakdown.
Yeah, the real reason he's telling this story.
Right. Sir Abrar Ali isn't just taking his audience on some nostalgic tour of 1970s analog relays. When you read the source, the way he leverages this history transforms the whole thing into a deeply psychological mission.
It really does. It addresses this pervasive, often unspoken issue in international engineering circles, the sociology of technology, basically.
Yeah, he is deliberately outlining this history to battle an inferiority complex that young engineers from his region often develop when they travel abroad for work.
It's a very real phenomenon.
He paints this incredibly vivid scenario. A young engineer travels to Europe or North America, walks into a state-of-the-art control room, and the foreign engineers start discussing these complex automated relay systems.
Right. And because the young engineer might only be familiar with the modern digital systems they trained on, and they haven't been taught their own localized history, they suffer a crisis of confidence.
Exactly. They assume their home country never possessed this level of foundational technology. Sir Abrar Ali explicitly says this lack of context makes them feel like they come from the quote-unquote third world or even 10th world.
10th world. Yeah, that phrase really hits hard.
It does. They internalize this narrative that they are perpetually decades behind, which makes them feel like imposters in those international boardrooms. They feel intellectually less than.
And imposter syndrome is difficult enough to manage on its own, but when it's amplified by geographic prejudice and a lack of historical awareness, it can just be professionally debilitating.
Completely. But by standing up and delivering this exact history lesson, by telling them, look, I physically stood in a substation in 1974 and wired these advanced Swiss relays at K Electric. We were running telemetry before 1970. He provides them with an absolute shield.
A shield of knowledge.
Yes. He's telling them that when those conversations happen in foreign control rooms, they can look their peers in the eye and say, yes, we had this in our system too.
He is arming them with their own intellectual lineage.
Exactly.
It proves to the global community, and honestly, more importantly to themselves, that they are equipped with modern, advanced knowledge that's built on a legacy of complex engineering.
Knowing how to calculate the trip setting of a solid-state relay is technical power, sure. But possessing the historical knowledge of how your predecessors built the analog foundations, that is raw confidence.
It completely redefines the purpose of technical mentorship. He isn't just teaching the physics of grid protection, he's actively inoculating his listeners against global prejudice.
Inoculating them. I like that.
Yeah, he's ensuring that when they walk into any facility in the world, they walk in as equals, fully aware that their regional infrastructure was pioneering the exact same automated triage systems half a century ago.
It is such a beautiful synthesis of engineering and human resilience. I mean, the core principles of load shedding that those 1974 relays executed, they remain the bedrock of today's digital smart grids.
The microprocessor just made the math faster. The philosophy of triage and the human ingenuity required to design it remains exactly identical.
We have really charted a massive journey today. We started with the sheer, unforgiving physics of the power grid. Massive metal turbines spinning precisely at 50 hertz, and the violent magnetic torque that threatens to literally tear them apart if that speed drops.
Yep.
We broke down the ruthless logic of the under-frequency relay, this automated sentinel programmed to execute instant triage, sacrificing radio lines to save the overall network from total collapse.
And we moved from the brilliant analog engineering of spinning aluminum discs in 1974 to the dense, localized history of K Electric pioneering early telemetry.
And we ended with a veteran engineer using that very history to cure a regional inferiority complex, turning a lecture on grid mechanics into a powerful lesson on professional dignity.
It really does reframe how you look at the infrastructure around you.
It completely reframes it. You look at towering transmission lines and humming transformers differently. Our modern world is utterly dependent on overlapping layers of invisible safety nets. Tripwires set to fractions of a hertz, designed by engineers decades ago, executing silent robotic triage every single day just to keep our routines intact.
It's humbling, really.
So the next time you rely on the power grid for something as simple as turning on the screen or heating your home, ask yourself, what other invisible guardians are quietly running in the background of your life? And how much hidden history, how much profound human ingenuity and hard-fought confidence are you walking past every single day without even realizing it?